Hello and welcome to part 3 of Laziness in Haskell. Today we are going to be answering some of the questions, not all, but some of the questions raised in the previous video. But before we jump into that, I wanted to take a moment to address a comment that was left on one of the previous videos. And I spent a lot of time thinking about it because I think it points out that some of the way that I've been using my terminology is perhaps not as precise as it could be, and it could lead to some misunderstanding. So here's the comment. And this person writes, the dual of lazy is not strict but eager. Strict and non-strict are properties of semantics affecting the result of the program. Lazy and eager are properties of the evaluation process affecting runtime resource consumption by the program. So I think what this person is saying is that really there's sort of these two axes here. And on one axis, we have eager versus lazy. And this is sort of a temporal thing. Something that's eagerly evaluated is evaluated immediately. Something that's lazy, we do something to delay its evaluation. And this is distinct from whether a language is strict or non-strict. And in a strict language, the order in which things are evaluated is very, very precisely defined, but it could be lazy, it could be immediate. And in a non-strict language, then the compiler has more leeway to evaluate things in whichever order it pleases. So most languages are kind of all the way in the upper left corner here. So if you look at a language like Java, for the most part, the relative order of evaluation is completely pinned down if we, again, ignore things like concurrency. Whereas a language like C is a little bit less strict, but it's still pretty strict. The compiler is free to evaluate, say, the operands to, I think, plus in whichever order it wants. And there's some examples like that, but for the most part, it's strict. And still, C and most languages are eager, which is to say they're not going to introduce suspensions. A language like Scala is maybe a little bit more towards the lazy side in that you can explicitly add laziness, and Scala allows you to introduce laziness but still be strict, which is to say that the order in which things are evaluated is still well defined, but there's some delay in which things are evaluated. And then all the way in the lower right corner, we have Haskell somewhere in there. And Haskell is both lazy and non-strict. Now, I think this is honestly a really nice way of thinking about things. And I think in many languages, this is the way that these terms get used. And in fact, I think in a previous video, I was using strict and non-strict to some extent in this sense. To mean strict means that evaluation is very sort of pinned down, and non-strict means that there's some wiggle room. But the truth is that this is a little bit confusing because when we're talking about Haskell, Haskellers use these words in a completely different way. So Haskellers think about this spectrum from strict on one end to lazy on the other end. And right away, we know that this cannot be compatible with this because here strict and lazy are two ends of the same line, whereas here they're on these orthogonal axes. So somehow these two definitions, or these two sets of definitions, are not quite compatible with each other. And I think that's really unfortunate and perhaps led to a little bit of confusion. So going forwards, and in this video and in future videos, I'm going to really try to be much more precise. And I'm going to say strict and lazy to mean strict and lazy in the Haskell sense. And in this video, we're going to get into sort of what that sense actually is. But in order to mean sort of strict and non-strict in this sense, I'm going to say precisely defined evaluation order versus less precisely defined evaluation order from the perspective of the semantics. So I'm going to try and do that consistently. Maybe I'll make a few mistakes, but I'm going to do my best. So this does still leave us with the question, though, which is what does strict and lazy mean in Haskell, if not eager versus lazy? And that's really what I want to talk about today, and hopefully answer the question of, could we have a imprecisely defined Haskell that is still perhaps eagerly evaluated? So already this terminology is coming in handy. So I think that the key thing that we need to think about if we want to understand evaluation in Haskell is demand. And that's really going to be the central focus of this particular video. So before we really jump into things and start talking about what is demand, I kind of want to open this video by presenting a little puzzle. And I actually posed this puzzle about a week ago to my followers on Twitter. And remarkably, almost nobody got it correct. Almost everybody got it wrong. Although I did kind of expect that. That's why I thought it was a fun puzzle. So the puzzle is, given this particular program, what happens when we evaluate val? So basically, if we actually look at what this program does, this is unfortunately a very stupid function. Many small examples often involve or require stupid functions, but bear with me. So we have this add maybe function, which takes an int and a maybe int. And what it does is, if the second argument is nothing, then we just raise an exception. And if it's just, then we add the first two arguments together. And then we have this val binding here, which calls add maybe with a exception raising expression. and then some nothing value. So if we sort of, I think, consider how most people would think about the evaluation of this program, then we could think about it very operationally. We could say that this is going to call add maybe. We're going to allocate a thunk for this expression. We're going to pass nothing. This first case, it certainly doesn't force the first argument. In fact, neither of these cases force the first argument. So we're going to match against nothing, and it's going to raise this add maybe exception. And so, we're definitely going to end up by raising this exception, and there's no reason to raise this exception here, because the only way that we could end up forcing this thunk is by calling plus, and plus would require the second argument to be just. So it seems very, very obvious, and indeed most people gave the answer, that this program will raise this exception, add maybe nothing to add. Now, what happens if we actually evaluate this in GHCI? Let's do that. So let's hop into GHCI and load our program and evaluate val, and indeed we see that we get the expected result. Nothing particularly shocking yet. It says add maybe, nothing to add. But let's go back into our program and let's make one change to it. Now, it's a little unfortunate that I have to do this, but I am going to add a no inline annotation here. And the reason for this is I want to illustrate what would happen in a real program if this were sort of a bigger function. So I know some people will say, oh, I'm cheating by adding this pragma here, but really what I'm doing is I'm trying to say, normally GHC is not just going to inline everything, but I'm using a small function as an example. So here, let's tell it to not inline this, so it can just call it as if it were a bigger function. And I'm going to save this, and I'm going to pop back into GHCI, but this time I'm going to enable optimizations. And so I'm going to enable the O flag, and I also have to pass object code, because otherwise it will just interpret the module as bytecode. So if we actually want optimizations to take effect, we have to pass this flag as well, but doesn't do anything other than enable optimization. So let's load things up again and evaluate, and now you'll see that we get a different exception. We get bang. We don't get the exception we got before, add maybe nothing to add. And if you look at this program, I think a lot of people are going to be totally mystified by that, because, Haskell is lazy. And the only thing that would force this expression is this x plus y expression here. And there's no way that we could evaluate that. So how could we possibly end up raising this particular error? Well, as it turns out, this is very closely related to what I said at the end of the previous video. Could we have a Haskell that is imprecise in the order in which things are evaluated, but still be strict by default, and how I think that Haskell kind of maybe already is that way? Well, this I think should maybe give you some reason to think that maybe we are, maybe it's not as simple as you think, and maybe that operational understanding of this allocates thunk and this forces it is not quite right. So in order to understand that, I'm going to put this example aside, and let's take a look at some simple examples. We'll come back to this later. So here I have written a perhaps excruciatingly simple example. We just bind 1 to x and 2 to y. We add the two numbers together. What do we get? This expression evaluates to 3. Quite unambiguous. No trick questions here. But let's change this program and see how this changes the semantics. So one thing we could do is we could introduce an additional binding here that raises an exception. What should this evaluate to? Well, if we were to say, operate in a traditional strict language, then this would, evaluate all of these things first, and then this would raise an exception, and then this entire expression would raise an exception. But again, as we kind of discussed in the previous video, if we are forced to evaluate everything, in that particular way, eagerly like that, then we miss a lot of potential optimizations. And in this particular case, one very nice optimization, because again, this could be some expensive function that then eventually maybe calls error, is we can just delete it. So, under the lazy semantics that Haskell has, we have this nice property that if you have some binding that's never used anywhere, then the program's behavior is not changed by just deleting the definition. So let's say, we want that. We want the compiler to be able to make that optimization. So we'll say that that's good and that's allowed. What happens if we try to change x to be an exception? Well, at this point, we pretty much have to raise an exception. There's nothing we can do to avoid raising an exception in this program. And the reason for that is that, well, x plus y, fundamentally, in order to produce a value for this expression, then we need 2 integers to add. And, we have 1 integer here in y, but x doesn't produce an integer, right? Its type is int, but it's kind of a misbehaving expression. It raises an exception. It's something that in Haskell we call a bottom. So bottoms are things like things that raise exceptions or things that just loop forever. And bottoms in Haskell have sort of a tendency to propagate outwards. So we would say that because this expression is a bottom, and because this depends on this bottom, then this entire expression is a bottom. And in particular, it's equivalent to just error x. So we could just delete this whole thing and replace it with error x, and that would be completely equivalent. And again, this is something where really no matter what semantics you use, whether you're using a lazy semantics or strict semantics, this program has to reduce to error x. There's just no way to reduce to anything else. Now let's consider a slightly different example. Suppose that we have x and y, and we make them both be exceptions. Now the question is, what is the meaning of this particular program? Well, here we can say that both of these expressions are demanded, so we can't just delete one like we did with z. But it's not entirely clear whether this program should raise this exception or this exception. In fact, it's very arbitrary. And so I think, again, keeping in mind that in Haskell, an exception, really means there's a bug in my program. So you wouldn't just have x equals error x, you'd have x equals some expression, and then somewhere deep down inside of it, some invariant violation occurs, and it raises an exception. Well, if it turns out that there's a bug in both x and y, I don't think we particularly care which one of them is signaled, as long as, one of them is signaled. And so in order to allow the compiler to, have some leeway in cases where we don't care, where we don't want to over-constrain our program, Haskell has what's known as a imprecise exception semantics. So what that means is if we have some expression and there are multiple bottoms that are demanded by that expression, then the compiler is free to choose which one sort of wins. So it's allowed to rearrange the program however it wants and evaluate it in whatever order it wants, so that this could evaluate to error x, or it could evaluate to error y. And these would both be entirely legal. Now, again, this I think is largely independent of the evaluation strategy we choose, because again, we're not really talking about funcs, we're not talking about suspensions. We're just saying, this particular expression must bottom, and that's because it depends on something that is a bottom. And what we really care about semantically is that we don't want the compiler to be able to transform expressions that don't bottom, which is to say expressions that produce a value. It would be very bad if the compiler rearranged things so that that did produce a bottom. So we're not going to allow that. And to be honest, the inverse is also true. If we have some code that says like, I want to raise an exception because some invariant was violated, which is to say the expression does bottom, then we'd be very unhappy if GHC deleted that check and the expression didn't bottom. So we want to preserve bottomness, but we don't really care about which bottom specifically is raised as long as, it's reasonable. It's not just some thing that it just pulled out of thin air. Now, at this point, I've just been talking about these cases where order of evaluation doesn't really matter, and we wouldn't even really think of it as mattering. But what would happen if we were to change this program to introduce a use of seek? So suppose that we write this expression here. So I think a lot of people would think that this does actually change the meaning of this program. They would say, well, okay, seek, I mean, it's even in the name. It sounds like it does some sequential evaluation, which honestly, I mean, yeah, I don't know why it's called that. It's very confusing. So they would think that x would necessarily now be evaluated before x plus y, and therefore this program's meaning is once again completely unambiguous. It's always going to raise this exception. But it turns out that from Haskell semantics, this is actually not true. What seek really does is it creates an artificial demand between an expression and some value. So what this is saying is that it's going to create an artificial demand between the x plus y expression and x. But in this case, x plus y already has a demand on x, which is to say, in order to produce a value by evaluating this, then this must produce a value. So this adds an artificial edge in the dependency graph, but it turns out that edge was already there, so it doesn't do anything at all. And GHC is still free to produce this exception or this exception. So where does seek actually matter? Well, if we were to have something like this, then having this artificial dependency edge would be very important. Or actually, I guess in this case, it's perhaps less interesting. Suppose we do this. So now it's unambiguous. This program is going to always evaluate to error z. But if we didn't have this use of seek, then that wouldn't happen because there would be no demand edge. We wouldn't be saying that this expression demands this value. It would just demand these two things, and so we would have the case we had before, we could just delete it. So what seek is really doing is it's a way for us as a programmer to add these sort of artificial dependencies to tell the compiler that in cases where, this particular expression wouldn't normally bottom, then we're basically telling the compiler that it's okay to make this overall expression raise an exception if this raises an exception, even if this doesn't directly depend on it. And in fact, it's actually stronger than that. It's not just that it's okay to raise an exception, it's that in this case, it is mandatory to raise an exception because, again, remember that it's not just that the compiler is prohibited from turning a non-bottoming expression into a bottoming one, but the opposite is also true. So because this has, this expression now has this artificial dependency edge on z, and z is a bottom value, then this overall expression must produce a bottom value. So GHC really does make a fairly strong guarantee that bottomness is preserved. Now, I know that this is going to come off as very surprising to people, and I think the reason for that is that most people view seek as sort of a thunk forcing operator. They think, okay, well, Haskell is lazy by default, so this is going to produce a thunk, and what's going to happen is that when we evaluate this call to seek, seek is going to force z here, and then it's going to evaluate x plus y. And because there's sort of that sequentiality, then if we were to have all of these raise exceptions, then the compiler would be mandated to raise this one first because, that's just what's going to happen. It's going to force this thunk before it evaluates this. But that's not really what's going on here. What's going on here is that seek is sort of really a static annotation to the compiler that says that, even if you can't otherwise determine that there is a dependency between this expression and this expression, then you are now mandated to pretend that there is a dependency between those expressions. Now, I think that because this is really sort of a static annotation and not really like a dynamic thing, the fact that it is in Haskell as a function is actually maybe counterproductive. Maybe it makes people get more confused. And that's why I actually prefer, and I think essentially all Haskell programmers prefer bang patterns. So this is completely equivalent. If I put a bang on z and remove this use of seek, then in fact, literally what happens is GHC just turns this into a use of seek. But I think it's a much nicer way to write it because what a bang on a let binding means is it means that we're introducing an artificial dependency edge between the body of that let and that binding. So we could also add bangs to x and y, but just as before, this is not going to actually change the meaning of our program at all because there's already a dependency edge between the body of our let and x and y. So all this is doing is adding those extra artificial dependency edges. Now, I really like talking about things this way in terms of demand rather than in terms of, laziness and strictness and when are things being evaluated. Because if we think about demand, then, ignoring this sort of artificial dependency edge thing, the question of which things bottom and which things don't doesn't actually depend on evaluation order. It's just the dependency structure intrinsic in our program. So the question is, why do we need to have this, ability to add these artificial dependency edges? Why would we want to add artificial dependency edges? Well, there's a few cases where it's useful. So let's take a look at them. So to start, I want to take a look at a very simple example. And again, this example is a little silly, but it's silly because it's small and it is sort of representing a standing in for a real program that you might want to write. So suppose that you're writing some data structure library and it has some internal invariant that you want to protect. And therefore, you have to protect that invariant in several functions in the library, and you want to sort of check it and report it in the same way. But it's just, a side condition. It's just an assertion. So you're going to write an assertion function that says, assert positive, and all it's going to do is take your data structure and it's going to return unit because you don't actually care what it produces. You're just running it as an assertion, as a side condition check. You're running it for side effects. And what we're going to do here is we're going to say, all right, if x is greater than 0, then we'll just return unit. And otherwise, we raise an exception, we bottom. And then when we actually want to use this, then we're going to use seek to say, I'm going to introduce an artificial dependency between this and this. Even though I don't use the result of this particular function, then I want the language to ensure that if this expression bottoms, then the whole expression bottoms. Now, I know in this particular case, we could actually just pattern match on the result of assert positive. We could say case assert positive n of and match on unit, and it would do the same thing. So, it's not strictly necessary here, no pun intended, but I think it's nice to be able to, sort of say in this particular case that we are not introducing a data dependency, we're introducing this artificial dependency. Now, for the second example, I'll confess I'm kind of dreading this a little bit because I think that I'm probably going to get more disagreements with this example than perhaps anything else I've ever said in any video, and maybe in any future videos. So we're going to take a look at foldl, and I know that a lot of people think, foldl, I have to write seek, It's, kind of the canonical example of that. And if you don't, it just leaks a bunch of space and that sucks. But I want to really ask you to approach this with an open mind, and we're going to think about it from perhaps a slightly different way. So first of all, I want to say that everything I'm going to apply doesn't matter whether lists are lazy or strict. This is just intrinsic to the structure of foldl. And I'd like to point out that f here, this argument to foldl, it's an unknown function, so we don't know the demand structure of f. We don't know if it depends on its first two arguments. Could just completely ignore them. We have no idea. And then what we're doing is we're doing this tail recursive structure with foldl, right? So on each iteration, we're kind of building up applications of f applied to s and some argument. So, this would be x1, the next two, and we end up, with sort of a nested sequence that looks like this. And so when we get to the base case, then if we're, not considering evaluation at all, then the dependency structure is just going to be f applied to f applied to f applied to f, s, x1, and then some long, long sequence. Now, if we just think about the data dependencies, again, not talking about evaluation order, we just talk about the data dependencies. This final base case is, again, the final demanded value. It's whatever demands the result of applying this function is going to demand that final result. And because we don't know the demand structure of f, we don't know whether or not those inner applications of f are actually going to be demanded. It's possible in theory that it could just, maybe sometimes throw its first argument away, in which case, we wouldn't actually need to evaluate some of those other things. And for that reason, since we never want our compiler, as we've already said, we refuse to allow our compiler to turn non-bottoming expressions into bottoming expressions, then based on the data dependencies that we've expressed in our program, then the compiler's hands are 100% tied, and it's not allowed to evaluate this expression too early. So how do we fix that? Well, we know that, in this particular case, the purpose of foldl, as we've written it, is to just accumulate some, value. The second argument, this s value, the state value, we're just accumulating it as we walk over our list. And for that reason, if this particular process bottoms at any point, if at any point it fails, then we're totally okay with the entire process failing. And so for that reason, we're going to introduce an artificial dependency edge between the result of this function and these intermediate results. And again, even if we don't talk about evaluation order, this does mean something semantically, which is specifically that each iteration depends on the iteration before it. Now, I know that when I say this, many people's reaction is going to be, but that seems the opposite of what I want. I want everything to be demanded by default, and then I want to explicitly opt out of those demands by introducing laziness rather than having to introduce strictness. But here's the thing, there is a fundamental asymmetry between those two things. Because remember that normally what GHC is doing is it is determining the dependency structure of our programs based on how values flow through the program. So it's trying to automatically make decisions about whether something should be strict or should be lazy based on the demands. But the only way to make everything strict is to just add a bunch of artificial demands, right? We've basically ruined our dependency graph. And so you can't then have your cake and eat it too. You can't say, well, I want the demand structure of my program to be dependent on, analysis of which things are actually used and which things are not, but then also say, but I want to assume that every single thing is demanded all the time. These two things are fundamentally in tension. And while it is true that there are some very special cases, doing tail recursion with an unknown function call of this form, where you do have to introduce artificial dependency edges because the compiler, doesn't want to break the semantics of your program, these cases are very rare. And essentially, when you're doing some kind of tail recursive loop with some accumulator parameter, then you just put a bang on it, and that's it, and you don't worry about it otherwise. So to really drive home to what extent this is true, where the compiler is really assuming that everything is strict by default, and it's introducing suspensions where necessary to preserve semantics, let's now finally go all the way back to this original example from the beginning of our program. And let's consider what would happen if we were to assume that this function were strict by default. We're going to assume that all of its arguments are strict. Then what we're going to do is we're going to say, okay, in the first case of the function, we do force this argument, but not this one, but the body of the function just immediately bottoms. So because this function just immediately bottoms, And because we're only prohibited from turning a non-bottoming expression into a bottoming one, since this one bottoms, then it's totally fine still to evaluate this argument, because if this one happens to bottom, then we're just changing the bottom, which is explicitly allowed. So we don't have to pessimize our program by introducing suspensions. Similarly, in this case, then trivially, x and y are both demanded. So once again, we can just assume that both of these are used, and it doesn't compromise on our obligations. So GHC has successfully determined that it does not need to introduce any suspensions in order to preserve the semantics of this program, and therefore it doesn't, and it just evaluates this immediately. Now let's go back and compare that example to this example from the previous video, where here we have or, and in this particular case, we can again start by assuming that everything is strict. We're going to start from that strict assumption, and we're going to say, in this particular case, this first case of this function, then this argument is demanded, but note that this one is not. And because this one is not, then there is a execution path through this function where it's possible to return a value, a non-bottom value, without demanding this argument. And for that reason, in order to preserve these semantics, in order to ensure that we don't accidentally turn a non-bottoming expression into a bottoming one, then this argument has to be assumed to be lazy. And of course, in this particular case, that's what we want. Now, this might seem like kind of a radical shift in perspective, because again, this process that GHC performs to determine, which arguments are strict and which arguments are lazy is historically called strictness analysis, not laziness analysis. But in fact, in modern versions of GHC, it is actually called demand analysis, which is a little bit more complex than just determining which things are strict or lazy. But the way that it really does work, the way that you perform strictness analysis is the way that I just described, is that you assume that everything is strict, and then you consider all possible paths through the program, and if any of them require laziness, then you pessimistically say, okay, that argument needs to be lazy. But again, because we're analyzing the dependency structures of our program, this tends to produce pretty good results most of the time. And it just turns out that there's these, pathological cases like foldl, where we have to help the compiler a little bit to understand our intent, because the straightforward expression of that function does not actually match our intent. Now, I'd like to start wrapping things up because I think this video is getting somewhat long, but before I close things off, I really do want to take a quick step back and make sure that we don't lose sight of the bigger picture, because we spent a lot of time in this video talking about these really small details about demand and seek and foldl and demand analysis, when really it's important to remember what the goal is here. The goal is that in Haskell, we want to be able to write high-level declarative specifications of our program. We want them to be efficiently executed. And what that often means is reordering and moving around the bits in our program. And so one of the things that I've sort of started saying, which I think is kind of a fun perspective, is that the goal of GHC is not to be a lazy functional programming language. The goal of GHC is to evaluate your program in the correct order. Now, of course, this leaves open what exactly the correct order is. But I think there's essentially two things that everybody can agree are important. One, we don't want it to evaluate our program in an order that breaks it. So we need to make sure that it doesn't turn bottoms into non-bottoms and vice versa. And we also want to evaluate our program based on the demand structure. And in Haskell, this is particularly wonderful because in Haskell, we are, a pure functional programming language. And what this means is that the demand structure is entirely encoded in the structure of our program itself, because there's no stateful side channels. You can't stuff something in a mutable array or in a mutable field in a class and then use it somewhere else. No, if you want to depend on something, it has to be an argument to the function. And so GHC is able to really look at our program and understand the demand structure and then pick an order of execution that both preserves the meaning of the program that we wrote and is most efficient. And if we go back to the example from the last video and really consider this particular example, again, we want to be able to write a high-level program where we say, okay, I want this to do something if this condition is true or this condition is true. But because GHC knows the demand structure of our program, then we ideally want it to sync this condition 2 closer to where it's needed, which is in the else branch. And again, this doesn't involve introducing any suspensions. It doesn't involve introducing any thunks. It's just about picking a evaluation order for a program that is somehow optimal. Now, it is true that there are some pathological cases, and I still haven't really broached that. I actually think that foldl is not a pathological case. I mean, maybe it's a pathological case in some sense, but I don't think it's that big a deal because, it doesn't come up that often. You just write some bangs. But there are definitely reasons that in Haskell, I think people, have this, it has this reputation of, it just creates all these funks, and we haven't actually gotten there yet. So in the next video, I think I will finally, stop leading you all on, and we will talk about why that is. And until then, I look forward to being flamed in the comments. So I will see you next time. Bye.